Hi, I'm Olivia, everyone's favorite math teacher, and in this video we're going to talk about something that's either going to be your favorite thing in calculus or your least favorite thing in calculus: optimization problems. So before we get started on the problems, I wanted to go over some general strategy here. Now, the first one I know is the same advice you get for every single question on every single test you've ever done. Read the problem carefully. The only thing I'm going to say here is the reason that I have it here, aside from the fact that it's good advice, is because on these optimization problems, they do get tricky because there will be a lot of situations in which there will be variables that are not required anywhere in the problem for calculation. They're only in the problem for setting up the parameters of the problem itself. And then there will be other situations in which there'll be a variable that isn't actually a variable, it's a constant. So when you're taking your derivative, that's going to be treated as a constant, and then something else is going to be treated as your variable. Now, on number 2, when we say identify the goal variable, this is the thing you are attempting to optimize. And I usually write it down because in the end, this is the equation we're trying to write. But I find that if we write it down, like this is what I'm trying to do, it helps me kind of keep my eye on the prize and I don't end up overworking a problem. Okay? Now, listing out the parameters, this kind of comes back from the read the problem carefully. After you know or you have a good idea of what you're doing, then listing out the parameters can help kind of keep an idea of what are my constants, what are my variables, what's going to be what's going to be a thing that I will take the derivative of, what's going to be a thing that might go away when I take a derivative, what's going to be, what's going to be in what equation, okay? Drawing a diagram. This is going to be vital for most of these kinds of problems. A lot of these problems are going to be physics or geometry based or trigonometry based, and all of those, a diagram is going to be exceptionally helpful. Even the ones that aren't necessarily physically based, a diagram can still be helpful because it can really help you see exactly how the variables are going to be working in relationship to each other and just kind of give you a bit of clarity here. And when I say a diagram or a few, that's because when you're working out how these problems work together, drawing a couple of diagrams can help let you know what kinds of answers might not actually work in your problem. So if your problem doesn't directly give you kind of boundaries, sometimes drawing your diagram goes, oh, I know that these kinds of ideas won't work because they fall outside of what's an acceptable answer based on how my variables are interacting, okay? Clearly defining your notation, that's just kind of the same clean idea that I talked about way earlier in our videos about what you should be doing in calculus in general. Now with these optimization problems, that becomes important because you'll want to make sure that you're identifying what is a constant and what is a variable. What are the things that you are going to be taking the derivative of and what you're going to be taking the derivative with respect to. And keeping that notation clean can be extremely helpful, especially if you're going to be doing things like using a change of variables, okay? And then this last one, it might seem like a meme when I say hit it with calculus until the answer falls out, but ultimately what this means is that after you've got everything set up and you start writing out equations, you're just gonna have to kind of try things, see what works, write some stuff out, try doing some derivatives, try putting equations into other equations, shifting things around, and trying to almost in a way work backwards from what our goal is. If our goal is to optimize an area with respect to a length, be like, okay, well, I only want to have lengths in here. So if my area formula includes a width, how do I get rid of a width? And then work your way backward from there, okay? One thing that I do want to say, and the reason why I write this the way I do here, is because one of the problems, I think, and one of the things where students get frustrated with these kinds of problems, is that these kinds of problems can take a little while to work through. It can take a lot of paper. There can be a lot of situations where you start doing something, hit a dead end, throw that away, and try something different. And unfortunately, if you try to get help with these from teachers, from tutors, from content creators, we make it look easy. And that's because we've probably done some of these problems 3, 4, 5, 6 times. So for us, it's easy because we've seen the problem before. And that means that even if we haven't done this problem for a year or two, we look at it and go, oh yeah. And it's like riding a bike. We go, oh, this kind of problem. You know, you can generally take this kind of a strategy, and then after a couple of steps, we're like, and that's how you solve it. And it looks like we just looked at the problem and we were like, oh, I'm a genius, and watch me wave my wand. Nobody solves them that way. I don't care what video you watched or how that person tried to present it like they were some genius or that whatever. Nobody solves them that way. Everybody had to work these out, had to go through struggles, and had to do it with difficulty. If anybody tries to fake it like they just knew the answer or they were just like, oh, well, watch, this is so easy, they're lying. Don't listen to them. That doesn't mean that people aren't smart. That doesn't mean that struggling doesn't make you smart. Every single one of these geniuses that we've talked about that invented all of this calculus we did, it took them years and it took a lot of struggle for them to do it. That doesn't mean that they're not geniuses that we don't laud for their great accomplishments, okay? Struggle. In the end, the struggle is worth it, okay? And anybody who claims that it wasn't a struggle for them, they're probably lying to you just for clout. So, hit it with calculus until you get an answer, okay? And practice, practice, practice. It's the best way you're going to get through these. Now, let's go ahead and hit some problems with calculus. So we're going to start with what's considered to be an introductory version of one of these kinds of problems. And this is pretty typical of the kind of problem you'll see of this nature. A farmer has some amount of fencing and they're wanting to enclose a garden or an animal pen or something, and one or more of the edges are a fixed structure of some kind. So in this situation, the farmer has 2,400 feet of total fencing and they want to enclose a rectangular plot with a stream as one border. Usually you're going to assume that that border is a straight line. And then what dimensions provide the most grass for his sheep in the enclosure? That last part is just a colorful way of saying maximize the area of the enclosure, right? Because the most grass is provided by the most area in that enclosure. So another way to read this is we have a certain linear measurement. Using that linear measurement, maximize a rectangular shape, right? We could write every single one of these problems that way, but that's less interesting. We like them to be somewhat colorful and applied. See if you can apply the general strategies to work this one out. And we'll work it together in 3, 2, 1. So here you go. Now, just like we did, we read through it. We found that we were looking for our A prime, right? And we were looking for A prime equal to 0. That would be our maximum. Now, we wanted to find the rectangular area, and we were given kind of a perimeter, right? Because we had that 1,200 feet to make the fence around. So from that, we knew the area would be a base and a height. We knew a perimeter would be a height and a base. And specifically for the perimeter, and this was important, we knew that it was going to be 2 for the height, but only 1 for the base, based on the diagram we drew. Because we were going to be calling this side the height and this side the base. And you easily could have changed up your diagram and called this the base and this the height, and that would have been fine. Wouldn't have changed anything other than how we did our notation. So this is what I'm talking about. Draw your diagram and be clear on your notation. And if your letters are different than mine, that doesn't change anything as long as your notation is clear and matches throughout your work. Because in the end, the answer should be the same. And when we work our way through here, you can see how our diagram and our equations, then we put that we have the P was 1,200 or 2,400 from up here. So then we relate these together and we go, well, we could have gotten rid of either of these. In this case, I chose to get rid of the H because for me that was the least amount of work because I didn't have to do any division. I just did a quick subtraction. And that's another kind of key thing here is I like to minimize the amount of work I have to do, and you'll find that throughout working on these, that's something that you'll notice, is that if I don't have to take a square root, I won't. If I've got an r squared sitting in a problem and I end with an r squared somewhere, I won't take a square root unless I have to. There's no need to, because I can use r squared over somewhere. I'll just keep it that way, okay? Then we get down to here, and at this point we have an a and an h, which means we can take the derivative of a with respect to h. So we go ahead and do that, and then we set this equal to 0 to find our maximum. Now, before we do this, though, we do want to do a cursory examination to make sure that we will, in fact, be able to find a maximum or a minimum. And in this case, a little bit of examination with our algebra brain tells us, well, absolutely there's a maximum. This is a quadratic function with a negative a, telling me that, yeah, the vertex is going to be a maximum because this is a downward-facing parabola. Okay, so we know that whenever we go to find that, and of course we could also have done our second derivative test if we wanted to, because if you take the second derivative here, that's going to be negative because that's a negative 4. A negative constant is always negative, obviously. But anyways, so set it equal to 0, and we get that that's 600. Plug that 600 back into our perimeter formula, and we got that our base had to be 1200. And then as an extra added bonus, we went ahead and found that area. The reason I did that is because sometimes these problems will actually ask you for what is that maximum. And again, since we had the formula there, I went ahead and just did that. Here's example 2. Go ahead and give it a try. It is just a little bit harder than the previous one. So, if 1200 centimeters squared of material is available to make a box with a square base and an open top, find the largest possible volume that such a box could have. I'll show you my strategy in 3, 2, 1. So I kind of split it up a little bit because of the chalkboard, but over here, we went ahead and defined what we're looking for. We're looking for v prime equals 0. That's our maximum. Then we've got our diagram. We've got our box that lets us know kind of what we're relating, our surface area. So I went ahead and drew my net, and then our box that kind of lets us figure out exactly how things are going to look. So our surface area, we've got our square bottom and then our 4 rectangular sides. Links those together. We've got our volume. And then we just go through and we do our calculations. This is a pretty standard problem that you might find on any kind of exam or a homework assignment, and it falls into what I would consider to be the more difficult end of the spectrum for these kinds of problems. Not because the calculus is more difficult, not because it requires any deep knowledge of geometry or trigonometry or anything else. There are a number of ways that you could approach this problem, but the reason that I think this kind of problem is difficult is because it's very easy to overthink. So give it a try and see what you do with it. And I'll show you what's considered to be kind of the standard solution to it in 3, 2, 1. So I hope you can see what I mean when I said that I'm not a fan of this question, because if you're one of the people that looked at this and then thought that you were needing to vary the size of the cut here, that's perfectly understandable. In a situation like this, yeah, I mean, you can honestly get to this answer using that method and you will arrive here. It will just probably take you a little bit longer depending on how comfortable you are working with arc lengths. However, like I said, this is kind of considered to be the standard way of solving this, using the slant length of the cone. And so we simply relate the height to the radius and then solve it through. And what we find is that the radius of the cut on the cone would be the slant length of the height. That creates the right angle here. We relate the two, and this is what I was talking about being efficient. So we find the h because we have the h here, but we also have the h squared because we have the h squared here, which gets us the r squared. I don't ever need to find r because I use r squared here. So I simply keep it as r squared, and then I put both of those values into my volume to find that my maximum volume in relation to that radius I'm given would be here. So I'm just going to do the outro here and not worry about giving you additional problems, since this entire video was simply doing problems. If you do have any questions, or if you're working on more of these, feel free to drop into the comments or join us on Discord. So I'll see you in the next video, and hopefully these are more fun than they are frustrating.